Hello, my name is Manoj Reddy Gurram. I am here to give a seminar on a deep learning model to predict thunderstorm. I am from third year electrical engineering. This seminar is made under the supervision of Professor Advait Mitra. So let's begin. What is a thunderstorm basically? A thunderstorm, also known as an electrical storm or a lightning storm, is a storm categorized by the presence of lightning and its acoustic effect on the Earth's atmosphere known as thunder. These thunderstorms are basically of three types, single cell, multi-cell and supercell. In these supercell thunderstorms are the strongest and most severe. Mesoscale convective systems formed by favorable vertical wind shear within the tropics and subtropics can be responsible for the development of the hurricanes. We saw what is a thunderstorm. Let's see why do we have to predict these thunderstorms. We know most of the thunderstorms are dangerous. Here, most thunderstorms pose the threat of heavy downpour. That means like heavy rains, gusty winds, and cloud to ground lightning. Sometimes, however, atmospheric conditions become favorable for particularly dangerous thunderstorms to form. These severe thunderstorms are defined as producing one or more of the following. Hail 3 by 4 of an inch in diameter or greater. This means like a hailstones falling from the sky. Wind gusts to 58 miles per hour or a tornado. It means when a thunderstorm becomes more and more powerful, these kind of things happen. Thunderstorms are dangerous because they include lightning, high winds, and heavy rains that can cause flash floods. And remember, it is a severe thunderstorm that produces a tornado. By definition, a thunderstorm is a rain shower that contains lightning. A typical storm is usually 15 miles in diameter, lasting on average of 30 to 60 minutes. Every thunderstorm produces lightning, which usually kills more people each year than tornadoes. That means like thunderstorms are more dangerous than tornadoes. How can we predict these thunderstorms? Historically, like meteorologists often often rely on massive computer programs called numerical weather prediction models to help them decide if conditions will be right for the development of thunderstorms. These models are designed to calculate what the atmosphere do at certain points over large area from the Earth's surface to the top of the atmosphere. Data is gathered from weather balloons launched from across the globe twice each day, in addition to the measurements from satellites, aircraft, ships, temperature profilers, and surface weather stations. You understand, right? From a lot of different places, we can gather data. The models start with these current weather observations and attempt to predict future using physics and dynamics to mathematically describe the atmosphere's behavior. This does not rely mostly on the computational power. Rather, it depends more on dynamics and mathematics and basically the relations between the elements in the nature. The predictions are usually output in text and graphs. This is a new way to predict whether a thunderstorm is going to occur or not. Let's see. Can we use a deep learning model to predict? What is deep learning? In deep learning, a computer model learns to perform classification tasks directly from images, text, or sound. Deep learning models can achieve state-of-the-art accuracy, sometimes exceeding human-level performance too. Models are trained by usually a large set of labeled data and neural network architectures that contain many layers. The input features were chosen primarily from for to predict thunderstorms. The input features were primarily chosen from numerical weather prediction. That means from the balloons and the satellites and from all those. The deep learning technique used to predict these thunderstorms is stacked denoising autoencoder in order to create a higher order representation of the features. After using SDAE, the output was then fed to logistic regression to make a predictive model. Let's dive further into the deep learning model. This seminar is based on a research paper that is published by uh, is based on a research that used deep learning model to predict thunderstorms in region of South Texas. Let me introduce you to this deep learning model. The objective of this machine learning technique known as deep learning is to predict thunderstorm occurrence up to 15 hours in advance, plus or minus 2 hours and 400 kilometers square accuracy. In particular, a deep learning neural network was used to post-process a deterministic numerical weather prediction model output to train and optimize a binary classifier. The NWP models historically have been used to predict the future state of the atmosphere and are essential with respect to predictions beyond 3 hours. However, these NWP models have many problems in them, such as discretization, truncation, and parameterization, introducing errors that grow during model integration. So a different strategy or a paradigm is sought in order to account for chaos in atmospheric prediction and errors in NWP output. Thanks to increasing availability of large data sets and affordable computational power nowadays, deep learning algorithms can now model complex nonlinear relationships in the earth sciences. So a deep learning can be uses computational power of a computer to uh, to form a nonlinear relationship between the elements in the nature, so as to predict the thunderstorms. So how do we exactly do this? First, let me introduce to the methodology. In methodology, first we have to know what is a model domain. Basically is a grid or an area where you want to predict the thunderstorm. So the deep learning model domain is represented as a 13 into 22 equidistant point with a grid spacing of 20 kilometers, resulting in a 286 box regions of area 400 kilometers. This is for the South Texas region that I took this seminar from the research paper. The deep learning models were trained over 286 box domain, while the results were analyzed for only for of the boxes. The three boxes were selected to account for the diversity of thunderstorm formation mechanism and the climate frequency of thunderstorms occurrence in order to assess the robustness of the deep learning models developed. So out of every three boxes, one three boxes were selected to assess the thunderstorm features. There are lot of features to consider, but here are the some of the important features that can be used as an input to deep learning model. Total predictable water in atmosphere. The short form is PWAT, and the units are very important. Here the for this units are millimeters, and relative humidity in percentage, mixing ratio of air in gram per kg, vertical velocity in meter per second. So there are a lot of features to consider while we are predicting a thunderstorm. What is a target? The target just basically means how can we say a thunderstorm has occurred? So we need a proxy that can say that if this happens, then a thunderstorm is occurred. So cloud to ground lightning was used as the proxy for thunderstorm occurrence. When a thunderstorm occurred, that just basically means there is a cloud to ground lightning has occurred. So a target vector was created that contained the number of CG lightnings, that means cloud to ground lightning strikes per date or hour or box for the study duration. The target was just basically defined as TDH. If it is zero, that means uh, that the thunderstorm was not occurred. If it is one, then the thunderstorm were occurred. Then we will discuss about the algorithm that is used to predict thunderstorms. Stacked denoising autoencoder that is employed in the deep learning model. Sometimes the performance of this is degraded by the increasing number of features. So there are a lot of features to consider while we are predicting. So we have to reduce those features. The problem is known as the curse of dimensionality. So as the more and more features we are considering, the model becomes more and more complex and its learning rate goes down. So extracting the features that are necessary to predict a thunderstorm is essential. Feature extraction or construction is a good alternative to reduce the dimension of input feature space. Presently available techniques typically consider the importance of each feature independently before selecting or eliminating them. So to extract features methods, there are various methods here. Some of them are listed like principal component analysis. This is based on a linear combination or non-linear dimensionality reduction techniques such as kernel PCA and autoencoder AES. Here. So mostly we use autoencoder AES nowadays. Here autoencoder AE is just basic. What does autoencoder AE mean? An AE network is a specific type of feed-forward neural network with a symmetric structure that attempts to reconstruct the output to resemble the input as closely as possible. So it decodes the output to reconstruct the input. So the AE includes encoder function that is responsible for mapping the input X onto the encoding Y and producing the reconstructed features R using the decoder function G. I will show you in the next paragraph how this is done. Here are the functions that are used for encoding and decoding. Here W means basically the weight of the each neuron and the bias of the each neuron. B means. In this, you can see from X input layer, we use a F encoding function to get this output. From this, we use a G decoding function to reconstruct the X, and we will get an R. From this R, we will try to update biases and weights. Internally, the AE hidden layer is also known as the bottleneck. That means this Y layer is also known as the bottleneck. The dimension of the encoding layer Y is selected based on the desired properties of the AE. It can be less than the input dimension known as the undercomplete AE or the higher than the input dimension known as the overcomplete AE. If the dimension of Y is less than X, then it is an undercomplete AE. Undercomplete AE representations force the AEs to learn most latent features of the input data while minimizing a loss function. So if the features of Y are less, then Y automatically selects the most important features of the X so as to reconstruct the R, so as to reconstruct the input. So an undercomplete AE will extract the important features of the data while minimizing the loss function. Here we can see how the loss function look like, where L is if for an undercomplete AE, nonlinear activation functions are selected for the encoder and decoder, the model can nonlinearly extract the most salient features of the dataset. Such AE models are also referred to as associative neural networks. These models can have overfitting issues and may require different validation methods than the common use of testing sets. As we are extracting them, these may sometimes overfit. So for this, we will use another kind of AEs, regularized AEs, to avoid the overfitting issue in AE. In addition to limiting the model's capacity by choosing an undercomplete structure, some regularization terms can also be added to the loss function to encourage the model to learn other properties of the input data. Regularization just basically means uh, adding a penalization weight decay or introducing sparsity in the representation resulting in the sparse AE. For a sparse AE, like for the most important features, a weight term is added so as to enhance its value in the prediction. For a sparse AE, a set percentage of the units in the hidden layer will be disabled by owing to the low values for the activation of the encoding layer. Weight decay enhances the generalization of training by amplifying smaller weights that produce good reconstruction. The weight decay term lambda is added to the loss function to quantify the magnitude of the decay and to limit the weight's growth. Here we can see to limit the weight's growth and to quantify the magnitude of the decay, a term lambda is added in the loss function. So finally, this is another kind of algorithm, stacked autoencoder. An SAE is an AE with more than one hidden layer. That means in the bottleneck layer, there will be more than one layer. An SAE takes advantage of all the benefits of any deep network with higher expressive power and computes features based on the greedy layer-wise training method. In this training method, the first layer of neurons, which ingests the raw input, is trained to obtain weights and biases that allows them for good reconstruction of the input layer. The output of the first layer is then used by the second layer to obtain its own set of weights and biases with the target to reproduce the output of the first layer. The process is repeated for potentially additional layers using the output of each layer as the input for the next and computing set of weights and biases to reproduce the output that of previous layer. So these are the various kind of the algorithms still we have seen. Now let's see experimentally how this DLNN works. The development of deep learning model began with the determination of SDAE architecture. Till now, we have discussed about the SDAE architecture. The output of this SDAE was then fed into logistic classifier consisting of two neurons and resulted in a binary classification, either 0 for non-lightning and 1 for the lightning. The output of the SDAE was then sent to a logistic classifier. So based on the output of the logistic classifier, we say whether a thunderstorm has occurred or not. The SDAE was trained based on the stochastic gradient descent and experiments were repeated 50 times to assess the variability of the process. The trained model was finally evaluated based on the independent test data. This experiment varied neurons in each layer from 1 to 100 determine the optimum number. So to determine the optimum number of neurons, we will vary from 1 to 100 and determine optimum number of neurons that gives us the most accurate output, while also varying the number of hidden layers from 2 to 3. So these are the parameters of the model. For the SDAE model, hidden layers we take from 2 to 3, neurons from 1 to 100, loss function mean square error, activation function sigmoid, optimization stochastic gradient descent, noise mask 15%, regularization parameter lambda 0.1 to 0.001, learning rate 0.0001, training epochs 500. That means the number of times we train the data. Training epochs means to determine the optimum number of neurons, a 95% confidence interval between based on the PSS metric and the standard error estimated based on the 50 iterations were used. This is used to determine the optimum number of the neurons. Here is the SDAE architecture. So here from you can see bottleneck layer with 3 neurons in between. The from that layer, the output was then sent to logistic classifier to predict the output. So here initially it encodes and then decodes by and recreates x1 dash, x2 dash, x3 dash. These are the reconstructed inputs. From these, we will update the weights and biases of the each layer. Uh, Here to avoid overfitting in the model, 15% noise was added only for the first layer to force the SDAE model to understand the latent features better. Also, a regularization term was added to decrease further the likelihood of overfitting based on the formula. By trial and error, lambda was set to 0.001. Using CE resulted in better performance while using a sigmoid activation function. Here, in principal component analysis, this is a linear combination, not the model that we are discussing. But from this, we can see the first 10 features approximately explain 90% of the variability. But in this first 10 features, in the top 3 features provide most 70% of the variability of the original data. So it depends on what kind of features we are selecting. So that will represent the max amount of data. Inputs consisting of both the first 3 and the first 10 PCA components were tested to predict lightning using a logistic regression classifier. Here, this is for the principal component analysis. But for SDAE, here we can see in diagram E, here first feature and second feature, we can see that most of them were third feature is not much used. Here, first SDAE feature was used in F. So as applied in PCA, the SDAE is learning low dimensional representation of data through dimensionality reduction controlled by the number of hidden neurons in the bottleneck layer. The information from the bottleneck is then used as the input into the classifier, resulting in improved performance by focusing the model on the most relevant information in the input features. So here we can see what are the important features that are necessary to predict the model from the diagrams of EFGH that are based on the SDAE. So how do we evaluate a deep learning model? To evaluate the performance of the deep learning model, the model was applied to independent dataset. Based on this, a confusion matrix for binary class, 8 different metrics were calculated. See, if the forecast was yes, that means a thunderstorm was happened and you predicted yes, then it's a hit. If you predicted no, then it said it is a false alarm. So it is the total is A plus B. A plus B means either if A is 1, B is 0, then it's a forecast. So if the forecast is no, but your model gave it as a S, then it's a miss. If the forecast is no and your model is said no, then it's a correct rejection. So from this, a confusion matrix is developed. So to get these are the evaluation metrics with which we evaluate our model. Probability of detection, false alarm rate, false alarm ratio, critical success index, Pierce skill score, high decay skill score, odds ratio skill score, Clayton skill score. From this, all these evaluation metrics are calculated. So we came to the conclusion. The particular deep learning technique used was stacked denoising autoencoder, a type of representation learning, whereby unsupervised learning occurs across a multitude of hidden layers in order to create a highest order representation of the original features as a pre-training step. The highest order representation of the output served as features used to train predictive models via logistic regression. The deep learning model performance exceeded substantially that of corresponding shallow neural network models. It can also be speculated that superior performance of the deep learning classifiers over the shallow neural networks is due to the ability of the SDAE to identify nonlinear combination of the input features that optimizes the performance of the subsequent predictive model. Thank you. Thank you for attending my seminar.